Kia ora koutou, no mai, haere mai. Welcome to lesson 16 for introductory physics. In this lesson, we're going to look at a new concept called momentum. And the idea behind this is that in the next lesson, we can then combine it with energy and start looking at a whole range of new phenomena called collisions. As usual, we'll jump over and have a look through the lecture. Lesson 16, momentum and impulse. Our goals are to define momentum, state and apply the law of conservation of momentum. That should be pretty easy now that we understand conservation from our energy discussions. Define and calculate impulse, and determine whether momentum is conserved or not in specific scenarios. So firstly, what is momentum? Do we have anything such as a conservation of velocity? Newton's first law tells us that if there are no external forces, then we have no change in velocity. So could we write this as saying that velocity is conserved somehow? If we have a system with multiple objects and the objects can interact with each other, then it's not quite that simple. When we've just got one object, Newton's law applies and we have a constant velocity, that's fine. But when we have multiple objects, we have to think a little bit more. So if the two objects are identical, we may have a scenario where that actually works. So in this case, you can see that the white pool ball is traveling with some velocity. It hits the other pool ball, it's sort of an orangey reddish color. That other pool ball then gains the velocity that the white one had and moves off with that velocity. They essentially swap velocities. One is at rest, one is moving, and then they swap, so the other one's at rest and the other one's moving with the velocity that the first one had. So it can happen in certain very special scenarios, but that's not very common. Usually it doesn't happen like that. Usually if the objects don't have the same mass, or if there's some other complication, as we usually get with real life physics, then they can't just swap velocities in the same way. The mass is a factor. If the two objects have different masses, then they definitely cannot. If they do have the same mass, then there's a chance it could happen like we saw just before, although even then it won't always. But the mass will definitely affect it. So perhaps there's a combination of mass and velocity we can use instead, and that will be conserved. There is, and it is called momentum. It is just simply the combination of mass and velocity, mass times velocity. Momentum here is written with the lowercase letter p. So please do be careful. Momentum is lowercase p, power is capital P, density is rho, which looks like it's sort of a curvy p. They are all very similar and they're all used in formulas where we may get them all. You'll also remember pressure was a capital P as well. So pressure and power are both capital P. Great, right? That's wonderful. You have to understand the scenario, think about what's being asked, and then none of it will be a problem because you'll always know what you mean by all the different symbols. Momentum is a vector. It is mass times velocity. Velocity is a vector, it has a direction, so momentum has the exact same direction as velocity, but the magnitude of momentum is determined by the mass times the velocity's magnitude. So mass times velocity gives us magnitude, sorry, mass times speed gives us magnitude, I should say, whereas the direction of the velocity is the direction of the momentum. There we go. Units for momentum, it is a mass times a speed, so it's kilograms times meters per second. That's it, kg m s to the negative 1. As usual, there are other valid units, but we'll generally stick with SI units just because we're going to deal with forces and momentums and energies, and keeping everything SI is the way to go. Momentum is something that people tend to have a fairly intuitive idea of. The idea that two things moving at the same velocity but with different masses can have very different inherent properties. Even if we haven't met the term momentum specifically, we still have this idea about it. And usually people have the right idea. If you ask people which of the two objects there, a toy car moving at 20 kilometers an hour or a real car moving at 20 kilometers an hour, which one has more momentum, which one is going to be a bit harder to bring to a stop, then usually everyone's going to say the real car because it's got more mass. More mass means more momentum, which means you have to use more force to stop it, essentially. If our system is a single rigid object, momentum is easy to determine because it's the product of mass and velocity. It's just mass times velocity, done. But what if our system is actually many objects, or potentially some object that is complex and has different parts that can move independently? What do we do for momentum then? Total momentum is simply the vector sum of all the individual momentums of the objects in the system. So if you figure out the momentum for every part of the system, add them all up, that's all you have to do. That is the total momentum of the system. They just add together. That's it. In order to do that, you need to remember that momentum is a vector. Momentum is a vector, so it has a direction, not just a magnitude. And you have to do vector addition. It may just be one-dimensional, in which case plus and minus is your direction, and it's very simple. But it may be two-dimensional or even three-dimensional, although usually in this course we won't get into three-dimensional stuff. But the maths is exactly the same between 2D and 3D, right? The idea is keep in mind that they are vectors. So if you have two momentums that are pointing in the same direction, that's easy, add them together. But if they're pointing in different directions, then you need to think about vector addition, and you're going to be using Pythagoras and SOHCAHTOA and all of that. Just as a quick example to hopefully really drill this home, two identical balls, one moving right with some velocity, the other moving left with the exact same speed. Right? So it's got the equal and opposite velocity, same speed, opposite direction. If we define our frame of reference as being right positive, then ball 1 has momentum mv, and ball 2 has momentum negative mv, because v is the speed of our first ball, negative v must be the speed of our second ball. So momentum 2 is negative mv, and that's just the negative of the momentum of the first ball. So then if we want to add them together, we just go mv plus negative mv, which is 0 kilogram meters per second. So momentum of that total system is 0. Each ball has momentum, but the total system of both balls has no momentum. Remember that we defined center of mass as being the average position of all mass. If we have two identical balls, then the center of mass is going to be right in the middle of those two balls, and it won't move. The center of mass will be stationary because the two balls are moving towards each other at the same speed, so the position exactly between them will stay in that same position the whole time. So we can actually think about total momentum of a system as being the total mass of the system multiplied by the velocity of the center of mass. So in our previous example, just to go back a slide for a moment, that center of mass is right between the two balls and it's not moving, so it's got a velocity of 0. So regardless of the mass of that system, because the center of mass is not moving, it has total momentum of 0. We won't usually go into any scenarios where this becomes particularly useful. Right? You can think about it. It is still a useful thought to have when you're doing that common sense approach. If something is symmetrical like that previous example, you would expect the total system to be 0 because that center of mass is not moving. So it can still be useful. It's still a good concept to keep in mind, but usually we'll be dealing with systems that are simple enough that we can just calculate 2 or 3 momenta and add them together. Let's suppose the two identical balls are now traveling in different directions. One is traveling straight up and one is traveling to the right. They still have the same speed, obviously different velocities because they have different directions, still have the same mass as each other. We now have one having momentum mv upwards and the other having mv rightwards momentum. To get the total momentum, we have to do vector addition because we're now looking at a 2D system. So we can't just add them. We can't just say the momentum is 2mv. This is one of the most common mistakes that is made when dealing with momentum. That's why I'm hopefully really drilling this home for you. You cannot just add momentum between different objects traveling in different directions, right? You have to do vector addition. Because it's symmetrical, we know that the two vectors are the same length. We know that the total momentum is therefore going to be at a 45-degree angle to the horizontal. And it's going to have a magnitude given by Pythagoras of the square root of 2 times mv squared. So mv all squared for each side of the triangle. So 2 of that and then the square root, which if you wanted to, you could mathematically simplify to the square root of 2 times mv. So vector addition, right? This whole slide is just repeating stuff you already know. It's vector addition is nothing new, just reminding you whenever you see momentum and you want to add momentum together to get total system momentum, you must do vector addition, vector mathematics. In that system, the center of mass is still always going to be right halfway between the two balls, but now the center of mass is actually moving. So let's go back for a slide, back a slide and have another look. The center of mass where the two balls are now would be right in between them. As they move upwards, the center of mass, sorry, this mouse is very sensitive to my hands today. As the balls move away, so the left, that one moving upwards and that one moving rightwards, as they move away, the center of mass would move along that direction illustrated by the total momentum vector that we've got there. They'd move along that line. So that center of mass is moving. So if the center of mass is moving, we would expect a total system momentum, and we'd expect it to be in the direction that that total system center of mass is moving. And that's exactly what we see. We see a total momentum of some magnitude, we don't know because we haven't been given numerical values, but of magnitude √2 times mv in the direction given by that red arrow. This next part of the lesson is going to talk about impulse, which again is another new term that we are defining. If the momentum of an object changes, what happened? Well, either the mass or the velocity must have changed. Usually it's the velocity. Technically we could have a change in mass, but we're not really going to deal with that in this course. So usually we are saying the velocity has changed, and it would be very clear from the scenario description as to whether the mass had changed. If nothing about the scenario has changed in terms of the objects involved, then that means that the mass hasn't changed. Change in velocity means acceleration. Acceleration means a force. A bigger acceleration, bigger change in momentum, bigger force. So these things are all related somehow. Impulse is how we relate them. Impulse is how much time a force was applied for. You apply a force for longer, then you're going to get more acceleration, you're going to get a bigger change in momentum. So impulse is just the product of force and time. How long was that force applied for? We often just write the full word impulse, sometimes the shortened version imp, IMP, or sometimes just the symbol capital I, but there's no general strict rule here, unlike some other terms. And a lot of the time we won't even bother writing impulse, we'll just write FT. We'll just write force times time. But you do need to be aware of impulse even if we don't have this agreed upon definition for the symbol. The units for impulse are newtons times seconds, force times time, Newton times seconds. But remember that newtons are also the same as kilogram meters per second per second. So we have newtons times seconds means we have kilograms meters per second times seconds, which cancels out one of those seconds and we get kilogram meters per second. The impulse has the same units as momentum, and that is hopefully a bit of a hint as to what our next statement is going to be, and that is that the impulse is equal to the change in momentum of an object. You apply an impulse, a force for some unit of time, that is going to give you a change in momentum equal to that impulse. So Ft is equal to delta mv or delta p. Remember, delta is change in. We already saw the units balance, so this equation is fine. If you apply a force to an object for some time, you're going to increase the momentum. If you apply the force for longer, you increase t. That means you're going to increase the momentum as well. If you apply a larger force, that would increase momentum as well. But if you apply both a larger force and a longer time, then the momentum change would be even greater. When we're trying to decrease momentum, we could achieve the same change in momentum by applying a greater force for a shorter time or a smaller force for a longer time. We often want to decrease the momentum over a longer time so the forces involved are smaller, such as when stopping a person within a vehicle during a collision. A large force can cause considerable damage, and so by taking longer to slow that person down, you can do less damage to them and they can receive fewer injuries. That's the purpose of cars crumpling, as per that image there. By crumpling the car, the person travels a bit further than they would otherwise, which means they can take a little bit longer to decelerate and the forces involved can be a bit less. Another idea is the one of bouncing. When you bounce something, for example, a ball falling downwards and then bouncing back up, it has the same velocity down as it does upwards. In reality, obviously, it would be accelerating, but we're going to pretend that we're just looking at the instant before it hits the floor and the instant after. Let's say it's traveling downwards with 5 meters per second and then upwards with 5 meters per second. You need enough impulse to change its momentum from mv downwards to mv upwards. That's twice mv. Whereas to just stop the ball, you just need enough impulse to change the momentum from mv downwards to 0, and that's just mv. So it takes twice as much impulse to make the ball bounce as it does to make it just stop. And that was used to great effect in the California Gold Rush by someone who designed the bouncing water wheel. The impulse water turbine is the name that they gave it, which is fairly generic because impulse is always present. This is just increasing the impulse by causing the water to essentially bounce. So I will jump over to the document camera for a moment and just try and hopefully make a bit more sense out of this impulse water turbine. Normally, when water hits a water wheel, so this is just the side view of the water wheel like this, water comes in, hits this, the water has a downwards velocity, and then it just basically stops when it hits this and rolls off. So it basically just stops, hits this, splashes off down here. And that way what you're getting is you're getting the impulse on each sort of water droplet enough to stop the water. And that impulse is coming from this paddle, which is obviously going to cause the whole water wheel to turn. And that's great. We obviously get useful energy out of that. However, what Lester A. Pelton realized is that if you instead make that paddle into a bucket that looks like this, then any water that comes in, any water as it approaches, will not just go and stop, it will be pushed back up. And so by pushing it back up, it won't be as great a velocity as what it approached with, because in reality we always lose a bit to friction and other things. But by pushing it back up, you're getting more of an impulse than you did here, which means the wheel is going to spin faster. Right? You're going to get more useful energy out of it. So that was his little invention, and it just demonstrates the utility of bouncing something. Right? The force, not the utility, but the difference in impulse required for bouncing something versus just stopping it. The next part is conservation of momentum. So we've already met conservation, and when we talk about energy, and momentum is the same idea. If you have no external force to a system, you can't change its momentum. Remember that you need a force to change a velocity. Right? Newton's first law says that if you don't have a change in, if you don't have external forces, you can't have a change in velocity. Momentum depends on velocity, so if we don't have any forces to change that velocity, we can't be changing the momentum. So that is just another conservation law. Just says without any external forces, you can't have a change in momentum. As our little example, just imagine a spacecraft traveling through space all the way out from everywhere, so there's no net forces on it, no effective forces, everything's negligible. It has mass and velocity, so it has momentum. Because there are no net forces on it, it can't change. It's just going to sit there floating through space at the same velocity and therefore with the same momentum. The law of conservation of momentum does allow us to solve a wide range of problems. The approach is generally going to be the same. You will either know the final momentum or the initial momentum of the whole system, or you'll be given the information to figure one of them out. Once you can figure one of them out, you then use the fact that momentum was conserved to figure out the other one. If you figure out the initial, you then know the total final is going to be the same, and vice versa. Often we'll need to figure out the momentum of one part of the system, or the velocity of one part of the system. So it's a matter of figuring out the total, initial, and final, and then breaking that down into the component momentums, all the while remembering that this is all vector mathematics, vector addition. So as an example, we have two balls bouncing off each other. The left ball has a velocity of 1.5 meters per second to the right, and a mass of 50 grams. The right ball has no initial velocity and a mass of 150 grams. They bounce off each other. The initial momentum is therefore given by P1 initial plus P2 initial. This is one-dimensional, so we can just treat it as right positive and left negative. So right positive means our first ball, P1, has an initial momentum of 0.05, the mass, times 1.5, the velocity, which is 0.075 kilograms meters per second. The second ball has no initial momentum because it's at rest relative to our reference frame. That means the total momentum of the system is just the sum of those, 0.075 plus 0, which is 0.075 kilograms meters per second. So that's our total initial momentum. From the law of conservation of momentum, we therefore know that the final momentum, after the balls have bounced, will be the same as the initial momentum. This is assuming there are no external forces. There's nothing else acting on these balls as they bounce off each other, just the balls bouncing off each other. That means that the total final momentum will be the same as that initial total momentum of 0.075 kilogram meters per second. Can we then determine the final velocities? No, we can't, because we don't know enough information. we know that the two final velocities will result in two final momentums, which add together to give that total final momentum. So we know m1 v1 final plus m2 v2 final is equal to 0.075 kilogram meters per second. We know that statement is true. But that's only one bit of information, and we've got two things we don't know. That's v1f and v2f. We don't know either of the final velocities. So we can't actually solve this. All we can say is the final total momentum will be the same as what that initial total momentum was, but we can't solve it yet. We would need one more piece of information. We would need to know either v1f or v2f, and then we could figure out the other one. So what if we know the small ball stopped after the bounce and the big one started moving? Then we know that v1f is 0, and we can solve for v2f, and that would give us the v2f of 0.5 meters per second. So if the small ball stopped, then the second ball, according to the law of conservation of momentum, would have to start moving at 0.5 meters per second. How about instead the two balls stick together somehow and they move off at the same velocity? So the two balls now have the same velocity. They were different to start with, and they now move off together with the same velocity afterwards. That means that v1f and v2f are both the same, and we can just call it vf, final velocity. We then can solve because we know m1 vf plus m2 vf is equal to 0.075, and vf is the only thing in that equation we don't know. So now we can just divide both sides by m1 plus m2, and we get out that the final velocity is 0.375 meters per second. So the balls would collide, and then they would move off together at that new velocity. What we see is that final velocities are constrained by the law of conservation of momentum, but there are still different possible outcomes. We need more information than just the conservation of momentum and initial conditions in order to know what will happen. As we just saw, both the ideas of one ball stopping and the other one moving off, or the two balls sticking together and moving off, they both work with the conservation of momentum. They can both still be true given the information that we had. So therefore, we often need more information about the system, about how the behavior is going to go, about how the objects will interact as they collide or as they bounce or as they do whatever they're going to do, in order to figure out what that interaction is really going to look like. And that's what we're going to look at in the next lesson. Another type of problem might ask simply if external forces are present in a given scenario. In such cases, you just figure out the momentum before and the momentum after. If they're the same, then there's no change in momentum, then there's no external force. But if they're different, then there must be an external force. That's the only way the momentum of our system could change. So as an example, two cars crash head on. One has a mass of 1,800 kilograms, is traveling with a speed of 45 kilometers an hour. The other has a mass of 2,300 kilograms and is traveling with a speed of 30 kilometers an hour. After the crash, the first car is at rest, and the second car is traveling back the way it came at 2.5 kilometers an hour. Were there any external forces on the cars during the crash? That's the question. First thing you should do is figure out your frame of reference. I know I've said at this point you should be sort of doing that implicitly, but I'm just going to mention that specifically here because this question doesn't really tell us the direction. It just says that it's a head-on collision. So all we know is that the two cars are traveling equal and opposite directions. Sorry, I shouldn't say equal. They're traveling exactly opposite directions. They would have to be for it to be counted as a head-on collision. So that's a bit of reading comprehension, understanding the scenario, visualizing it, and thinking about what's going on. So we've got two cars traveling directly towards each other. So now you can realize it's one-dimensional. You can choose your positive and negative. So I'm going to call the direction of one of the cars positive and the other one negative, and we can figure out everything that way. So as I said, frame of reference is the first thing to do. Initial momentum, the first car is positive. So 1,800 times 12.5. Remember to convert to SI units. Always convert to SI units because momentum and newtons, when we move into forces and things and into energies and stuff, sticking with SI units is just the cleanest way to go about it rather than having to worry about trying to convert some kind of kilogram kilometers per hour into something that we can turn into a force if we had to do it. We don't have to in this case. So you could theoretically do all your momentum in kilogram kilometers per hour, but it would be a bit strange. So the initial momentum is positive direction, 22,500 kilogram meters per second. The second car, it's traveling in the direction we've defined as negative. So its momentum is going to be negative 19,200 kilogram meters per second. that means our total momentum, we just add them together. Because it is vector addition but one-dimensional, that plus and minus are our directions, so we can just add them together, and it's 22,500 plus negative 19,200, which is 3,300 kilogram meters per second. Our final momentum then, we're not using the conservation of momentum here. We are using the final conditions that were given to us, and we're going to compare it with the conservation of momentum. So our final momentum, the first car is traveling at 0. The second car has a velocity now in the positive direction, and it has therefore a momentum of 1,600 kilogram meters per second. I haven't written in the final total momentum, because hopefully you can see that this is going to be equal to that second car's final momentum, because the first one has 0. So P total final is just 1,600 kilogram meters per second. Therefore, the system has lost momentum. It's gone from 3,300 down to 1,600. So there must have been an external force acting on the cars during the collision. And in the case of a car crash, it is most likely going to be friction. Note that it's not going to be the crumpling of the cars or anything, because that's all internal to the system. Right, that's all internal to the system. Even if the cars crumpled together, if they were in a perfectly frictionless environment and they crumpled and stuck together in one big massive twisted car, that would still have that same final momentum as the initial momentum. If there was no external force, that momentum would not be able to change. Therefore, we must have an external force, and it is going to be friction between the tires or other car parts and the ground. So that's the end of this lesson, which has just introduced the momentum and impulse. As I've said, that now sets us up nicely to look at collisions in the next lecture. So collisions are basically what we just saw, with a couple of balls bouncing off each other or a couple of cars crashing into each other. Those are collisions, when you get two objects that interact with each other. And we can use the idea of energy and momentum and how both of them are conserved in different scenarios to figure out what happens in different collisions.